Today, we are diving into one of the weirdest, most profound, and honestly, most beautiful ideas in all of physics. It's called the Aharonov-Bohm effect. It's a phenomenon that, on the surface, seems completely and utterly impossible. But when you dig in, it reveals a hidden truth about how the universe is put together. It's just amazing. So let's get right into it.
Okay, so I want to start by asking you a really simple question. Think about it. Can something influence you, change your behavior, alter your path, if there is absolutely no force, no contact, no physical interaction between you and it? I mean, your gut reaction, your common sense, it just screams no, of course not. But as we are about to find out, the quantum world, well, it plays by a very different set of rules.
And right here, this is the heart of the puzzle. On one hand, you have the rules of the world we live in, right? Classical physics. If a magnetic field is zero where you're standing, it can't push you, it can't pull you, it can't do anything to you. It's not there. Simple. But then you have this absolutely bizarre quantum prediction that a particle can somehow feel a magnetic field that's somewhere else, in a room it never ever goes into. How on earth is that supposed to be possible? So to figure out how that's even remotely possible, we need to go back to the beginning, to the origin of this idea that, by all accounts, just shouldn't exist. Yeah, the whole story kicks off back in 1959. You've got these two physicists, Yakir Aharonov and David Bohm, and they're just looking at the math, at the core equations of quantum mechanics, and they realize the math is telling them something that just flew in the face of all classical logic. They predicted something that really, truly should not be able to happen.
Okay, so a wild prediction is one thing, but actually seeing it happen in a lab, that is a whole other story. So let's take a look at how physicists actually managed to build an experiment and observe this impossible effect. The setup is actually a really clever twist on the classic double-slit experiment. You start by firing an electron. Because it's a quantum particle, its wave splits and it travels down two separate paths at the same time. Now here's the kicker. In between those two paths, they placed a long, perfectly shielded magnet. It's called a solenoid. You can think of it like a perfectly insulated pipe. The magnetic field is 100% trapped inside that pipe. The electrons only go on the outside. They never touch the field. Then the two paths come back together and hit a screen, and you get that famous interference pattern.
And I really want to hammer this point home. Along the electron's entire journey, both paths, every single point, the strength of the magnetic field it experiences is exactly, precisely zero. There's no magnetic force pushing or pulling on that particle at all.
And yet, when they run the experiment, this happens. The interference pattern on the screen actually shifts when they turn the magnet on. It's just undeniable. The electron acts as if it was pushed by a force, even though we know for a fact no force was there. It's like somehow the electron knows that the magnetic field is hiding inside that solenoid.
You know, to really get a handle on how strange this is, here's an analogy. Imagine walking down a hallway, and you pass a perfectly insulated, totally sealed room. The Aharonov-Bohm effect is like feeling the heat from a raging fire inside that room, even though zero heat is actually leaking out into the hallway. In our everyday world, it just makes no sense. And you might be thinking, okay, maybe this was just a fluke, a one-off experimental error. Well, not a chance. This thing was first confirmed in 1960, just a year after they predicted it. The really definitive proof came in 1986, when a team used a practically perfect shielded magnet that left no room for doubt. It's been confirmed over and over since. This isn't a quirk. This is a real solid feature of our universe.
So, if it's not a force, then what in the world is going on? Well, the answer, it turns out, was hiding in plain sight. It was in the mathematics of quantum mechanics the whole time. See, in classical physics, we always thought the magnetic field itself was the real thing. There's this other mathematical tool called the vector potential that we use to help calculate it, but we always thought it was just a trick, a mathematical shortcut. But quantum mechanics comes along and completely flips the script. It tells us that this vector potential, it isn't just a convenience. It is physically real, and it can be out there doing things even in places where the magnetic field it's supposed to describe is totally zero.
So what is this vector potential? Probably the best way to think about it is like the source code for the magnetic field. The magnetic field is the final program you see and measure as a force, but the vector potential is the deeper mathematical structure that creates it. And here's the truly mind-bending part. This source code can exist, it can stretch out into regions of space where the final program, the magnetic field itself, has been completely canceled out to zero. The underlying information is still there,
even if the force isn't.
And this, right here, is where the story takes this absolutely breathtaking turn. Because the vector potential isn't just some new kind of field. It's a clue that physics might not be about forces at all. It's about geometry.
Okay, to get our heads around this, we need a cool concept called configuration space. Don't think of it as just the normal 3D space we live in. Imagine it's this huge, abstract map of every single possible path a particle could ever take. And what the Aharonov-Bohm effect shows us is that putting that solenoid in the middle doesn't create a force. It literally changes the shape of the entire map.
And this is the big aha moment. Look at the left. With no magnet, the space is simple. Any path an electron takes from A to B can be smoothly wiggled around and turned into any other path. But now look at the right. When we add the solenoid, it's like we've punched a hole right through the fabric of space. Now a path that goes to the left of that hole is fundamentally different from a path that goes to the right. They are topologically distinct. You can't turn one into the other without going through that forbidden region in the middle. And that leads us to this massive, world-changing idea. The electron isn't being affected by some spooky, long-distance force. No, it's simply navigating the space that's available to it. And the global shape of that space, the overall geometry, is different just because the solenoid is there. Physics isn't just about local pushes and pulls. It's about the global geometry of the whole system.
So let's connect all the dots here. That vector potential, A, it isn't a force. It's the map. It's the mathematical language that describes this new, weird geometry with a hole in it. And that strange shift we see in the experiment, that's just the physical evidence that the electron's two paths had different geometric lengths as they navigated around this hole in space. Now, this isn't just some clever way to solve one weird quantum puzzle. This geometric way of looking at physics, it has implications that literally change our understanding of pretty much everything. Just look at how this reframes the whole problem. Where we used to have to say, well, I guess the vector potential is a real physical thing, we can now say something much deeper. The configuration space itself has a complex shape. The effect is topological because that solenoid creates a literal, uncrossable hole that changes the rules of the entire space around it. And we're not just talking about electromagnetism here. This core insight, that physics is fundamentally geometry, is the bedrock for our entire modern picture of the universe's fundamental forces. Gauge theories, the theories that describe the weak and the strong nuclear forces, even our best theories of gravity, they are all built on the same incredible principle. Forces are just what we see when particles move through curved geometric spaces. So, a big question you might have is, wait, does this mean physics is non-local? Is this that spooky action at a distance Einstein was so worried about? And the answer, amazingly, is no. The real beauty of this geometric view is that locality is perfectly safe. The electron isn't interacting with the magnet far away. It is interacting locally, at every single point on its path, with the geometric structure of the space right where it is. And that is the profound, beautiful takeaway from all of this. The universe isn't some boring static stage where forces come along and push particles around. No, the stage itself, its shape, its topology, its geometry, is an active player in the game. There's no spooky action, there's just the intricate, elegant geometry of configuration space and particles just moving through it, following the rules.